Hi, this is group 1, and now we are going to look at the output voltage of the waveform generator.
This is ground, and this is the output wire from generator.
It's around 1.9 volts.
2.9 volt.
Yeah, 2.9 volts. And use that figure, we can get the theory output value of the current pump, would be 0.3 milliamperes. Since the load we use is 4.7 kilo ohms, we can now look at the real output voltage. It's around 1 volt. And the theoretical value is 1.5 volts. There is some error because of the LC filter we use. The serial impedance of the inductor may hazard this output current. Now we are going to adjust the frequency of the output.
Frequency. So now the frequency is around 6 kilohertz. We can decrease that. Oh, we can slightly decrease. To actually 1 kilohertz. Yeah.
Also, the amplitude of the output current can be changed. Theoretically, it should be from 1.17 volts to 2.35 volts.
So here is 1.17 volt. You can up to
2.35.
2.35. Yeah.
The output waveform can also be changed from sine wave to triangle wave. We use a filter here to filter out the noise. Now let's see what it's like when we do not have the filter. You can see there's a lot of noise here. The line becomes thicker.
You can see lots of noise.
A lot of high frequency noise. And it's the same with the sine wave here. We do not want that. Hi, now we are going to test whether this device can measure the impedance of a kiwi fruit. The input current we use is like the previous is 0.25 milliampere. And the voltage here is 1.03 volts.
So 1.03 minus
Divided by 25. So the impedance should be 4.12 kilo ohm.
and now we can also test the water.
You can see here the voltage is also around 1.3 volts.
And if I increase the distance of the water of the electrode,
We can clearly see that the voltage has increased.
And if I close this electrodes, the voltage is decreased, and it's increased, decreased.
Hi, this is Group 1, and now I'd like to talk about the limitation of our EIT system. The first one is there's no DC offset change. Since the DC offset is achieved by a subtractor, and the subtractor's input voltage is fixed by a voltage regulator, we cannot change the DC offset. Probably we can change that by using a buck boost converter. Second thing is there's no square wave. This is because by designing we get. The third thing is there is no decent amplitude or frequency control knob. We used a chip port resistor in the PCB, and it is controlled by a screwdriver. And the fourth thing is there is a load range within the saturation, because all the op-amps cannot produce the output higher than the power rail. So there's a limitation of how big the current can be driven and how big the load can be. And the fifth thing is there's frequency and amplitude range. The range is shown here. It should be known that the actual sinusoidal current range is slightly larger than the theoretical sinusoidal current range. I think this is because we cannot detect the perfect sinusoidal wave from our bare eyes from in the oscilloscope. This is our group distribution.